Hello dear members of the jury, dear audience, dear internet public. We are presenting you our solution to the problem Gee-Haw Whammy Diddle, or the HUI machine. Slide please. So, in reality we are presenting you actually the TOMOV-DIMITROV eigenstate superposition in theory. So, the reporters are Dimitar Tomov and
Ivan Dimitrov.
Slide.
So now let's recall the problem statement once again. A Gee-Haw Whammy Diddle is a mechanical toy consisting of a simple wooden stick and a second stick made up of a series of notches with a propeller at its end. When the wooden stick is pulled over the notches, the propeller starts to rotate. Explain this phenomenon and investigate the relevant parameters.
So, our theoretical background considers that capturing a video of the toy being propelled leaves us with the opportunity of obtaining angular velocity graphs of the propeller with respect to the nail. We can see one here, and we can see several important aspects of the graph. So first of all, we have the discrete levels of the angular velocity, and second of all, we have a very important state in the middle where we observe two states at the same time. Slide. Our theoretical model consists of modeling the propeller as a quantum oscillator with ground state angular frequency, the omega ground. We can derive the expression for the energy of each discrete level as this expression, where Kc depends on the fundamental physics constants involved in the process and the propeller parameters. And h of n is corresponding to the energy level as a function of the index of the discrete level. Right? So, what is superposition, you might ask? From the experimental data we conclude that the upper two segments of the graph here correspond to a superposition of two energy levels, the one here and the one here. We can then determine the angular frequency of the superposed layer, which is in the middle, showed in the green line, as this expression. And we also know that this superposition and the lower level, with omega n, are two consecutive discrete energy levels.
So, it is also known that the angular frequency of such an oscillator depends on the ground angular frequency and the function h as a function of n. So from here we can rewrite the following formula as a function of the angular velocity in the current state, and we can express the function of the energy level n index as a function of the current angular velocity and the ground angular frequency of the oscillator. So we have a one-dimensional quantum oscillator here because our propeller only rotates based on the nail's position, and we have only one-dimensional rotation, which is only a function of the angle of declination of the nail's diameter and of the propeller's diameter to the nail, and thus our quantum oscillator is also one-dimensional. And from here we can rewrite the formula for the levels index as follows. And we can obtain the coefficients A and B, which characterize the linear dependence. So, the lowest energy level which we observed is at omega equals 300 radians per second. So, by substituting in the formulas for A and B, we can obtain the coefficients, and thus we can also obtain the function which characterizes the energy level, which is given with the final formula on the slide. Now, we can also rewrite the constant Kc. It is proportional to the basic physics constants, which is only the gravitational acceleration on the Earth's surface, and the propeller's dimensions, which are its mass, its length and width, and also the ground state angular velocity. So we can finally obtain the final formula for the discrete energy layers, which is shown here on the slide. So what will our propeller actually do? When we start spinning the propeller, it spins at some constant angular velocity omega. So the energy of the propeller will be given with this formula here. However, for the quantum oscillator, we have the following formula for the energy layers. So that means that our propeller will jump an energy layer and increase its angular velocity to the angular velocity corresponding to the nearest energy level, which is with a lower energy than the energy we have here. This means that by accelerating the rate at which we rub the stick, we will thus accelerate the angular velocity of the propeller, and at some time it will jump and it will increase from a lower value to a greater value almost instantaneously, because we have discrete energy levels for the propeller. So here in this formula, this coefficient I is actually the propeller's moment of inertia.
So you might ask what a demonstration might look like, and with considering our great theory of superposition of the two states of the angular frequency of the toy, we might show you a demonstration of the process. Mr. Dimitrov, please hold the toy, and you take a stick and you propel the toy.
Not too much physics was violated during the shooting of this video. Feel free to copy and redistribute this material in any medium or format as long as you cite the work as TOMOV-DIMITROV EIGENSTATE SUPERPOSITION. Enjoy.